que viene de la Universidad Autónoma del Estado de México. No, ya no. Bueno,
ya no.
Voy a hablar de la concepción temprana de las matemáticas de Bolzano.
Sí. First of all, I want to thank to Carmen and Carlos for the invitation, and to all of you. And so, I will talk on Bolzano's early conception of mathematics, and by that I mean his conception of mathematics till 1817. Okay, that is until the publication of his rein analytische Beweis, of his purely analytical proof. So, to begin with, I will quote his definitions of mathematics, beginning with the one that he presents in the Beiträge, his contributions to a better grounded presentation of mathematics from 1810. And there he says, mathematics could be best defined as the science which deals with the general laws, forms, according to which things must be regulated in their existence. And so this is the definition around which I will be talking today. But before doing that, I want to talk a little bit about his later definitions. That is the one he presents in his theory of quantities, written in the 1830s, where he says, the traditional definition of mathematics that has been given up to now does not say anything else than that mathematics is the science of quantities. That is the traditional definition of mathematics. And then, later, just to be sure that he was keeping that traditional definition till his last day, in the new Anti-Kant, written by Prihonsky, but with collaboration of Bolzano, one reads, to us, mathematics is the science of quantity. So far it seems that there was a big shift there between 1810 and the 1830s.
When you say quantity in German, it's grossen? Or
Sorry. Yeah. I'm translating grossen. Yeah.
magnitude?
No, I'm translating. Yeah. I know. Okay. Yeah. Maybe we can talk about this at the end. So, as I said before, let me say a couple of things about his later conception of mathematics. So about Bolzano's late stance. What is the notion of quantities underlying his traditional definition of mathematics? Well, it's not the traditional definition of mathematics. He says, for example, in his theory of quantities, in a narrow sense, one could understand by quantity what one usually calls continuous quantities. In a broader sense, one could take the word to include both the continuous and the so-called non-continuous or discrete magnitudes, and nothing else. In its broader sense, we call any object a quantity when we consider it as belonging to a species of things. Between any two of those, we can assert one and just one of the following reciprocal relations. Either they are equal, or one contains a part that is equal to the other. A similar definition of quantity can be found in his theory of quantities, published in 1837. And then, just to say a little thing more, in his paradoxes, written between 1847 and 48, but published in the 51 by Prihonsky, precisely, he wrote, not only are all numbers also quantities, but there are even more quantities than numbers, because also the fractions and the so-called irrational expressions designate quantities. So what I want to point here is the fact that while he preserves the traditional meaning of an appellation of the appellation number, but preserves the expression of the traditional definition of mathematics, he changes the meaning of quantity. So it's not exactly the traditional definition of mathematics, the one that he's defending later. But also, concerning this, Paola Cantu precisely defends in a paper of 2010 that this is not a U-turn in Bolzano. She argues that Bolzano is constantly talking with Kant there. And so there is no U-turn there, but only a shift of stance against Kant. That's her position. But while I'm quoting Cantu because I agree that Bolzano is constantly talking with Kant in some aspects. And this is important for me for what I will explain of his early conception of mathematics. But we also have this quote from the seventh section of his Großen Lehre, that is his reine Zahlenlehre, where he says, the infinite number concept which the expression S designates is measurable. This is an example of an infinitely small positive number. This is surprising for a reader of Bolzano because in his early works, he said this: calculus is based on the shakiest foundations, for example, on the self-contradictory concepts of infinitely small quantities, which are smaller than every conceivable quantity. This is from his work of 1816 on the binomial theorem, but it is precisely the point where he introduces his notion of variable quantities omega, which normally are understood as an early version of the epsilon delta definition of a limit. No? So there is that. And then, some authors, as Ross and Rifayova, have pointed out that precisely this shows that by the 1830s, he had already gone a long way towards developing a bold, original framework for a theory of real numbers. So that's the late Bolzano, just to have it clear. And now I'm going to explain what happened before this. So, what are quantities, what are forms, and what are things for Bolzano? Because we read his definition. Mathematics is a science which deals with the general laws, forms, according to which things must be regulated in their existence. And so, for him, a thing, he says in his Betrachtungen, that is his first work, his considerations on some objects of elementary geometry from 1804, he says, a thing is called a quantity insofar as it is regarded as consisting of a multiplicity of things which are equal to the unit or the measure. This was a common understanding of quantity. But then he says, he's discussing in this work, at the beginning of this work, he's discussing the notion of mathematics. And so, before offering his definition of mathematics, he discusses a couple of definitions, Kant among those. And then he says that defined that way, quantity does not exhaust the content even of this science. But then he quotes a definition of Franz von Ritter that says that quantity is something that exists and can be perceived by some sense. And Bolzano says, this definition, by contrast, is either too wide, that is, in the wider sense, in the broader sense, mathematics would embrace all sciences, or most, and then, or too narrow. So mathematics would only be concerned with empirical things, no? If understood in the narrow sense, the sense. So That's concerning quantity. But then what about form? He says form is a general law, that is, a condition for the possibility of things. And so this sounds like someone talking a little bit with Kant or the Kantians of the time. And he says that by things, here in his definition, he is understanding those with objective existence independent of our consciousness, either as individuals, that is, intuitions, or simply as general concepts, and also he is understanding by things those objects of thought. Okay? So these are the things that the forms, the laws in the definition of Bolzano are referring to. It must be noticed the way he identifies individuals and intuitions, because that's a key point of his critique to Kant, precisely. And then he says, or general concepts. No? So there's a certain opposition between intuitions and general concepts. These concern individuals? Yes, Axel.
How strongly are we supposed to read the regarding? So quantity is a way of regarding objects, or is a kind of object?
Quantities.
Yes, because it says,
yeah.
It is insofar as it is regarded as blah blah blah. So does that mean that this quantity is a way of looking at things?
Yeah, a general concept. Yeah, exactly. Because his point.
Not that the objects themselves.
No. Because his point is that not everything that mathematics studies are quantities, precisely. And here he's thinking in combinatorics by the time. So you have to think that the Hindenburg combinatorial school that Eduardo is here, the specialist, but you have to think that we are talking about the beginning of the 19th century, and in the Germanic mathematical context, there was, this school was successful among certain authors, no? So Bolzano is not only talking with Kant, that is part of my point, but also is sharing some things with the combinatorials, with Hindenburg combinatorial school. Okay? So yeah, that's... So, we can ask ourselves if there are similar definitions, because, we have this definition, this traditional definition of mathematics as the science of quantity, and then if we look for definitions similar to Bolzano, the one of Bolzano, concerning forms, we can find some of them, but let's look at them. The first one that he quotes of Kant, mathematics is the knowledge of reason. Here I might not be translating perfectly, so there's, I'm looking at Abel because I consider him the reference here. So, from the construction of concepts. But then, there's another author, Schultz, which is a main reference for Bolzano concerning foundational issues. Okay, so I will go back to this author. But Schultz wrote, general mathematics abstracts from the various qualities of quantorum and investigates the ways in which homogeneous can be connected or units can be composed into wholes. So this is a different conception of mathematics, and it paves the way to a different classification of mathematics, because the usual classification of mathematics, for example, the one of Kessner, would regard general mathematics or pure mathematics and then divide into geometry and arithmetic or algebra. And this is different. Schultz here is saying something different. And then Bolzano quotes an anonymous reviewer from the 1808 that Paola Cantu says that it's Bolzano himself, but me and Johann Bloch, we said that it's not. He is not. So, an anonymous reviewer. Quantity is only an object of mathematics because it is the most general form. But it is, in its nature, mathematics is a general theory of forms. This is the most similar definition by the time to Bolzano's. But then we can also find precisely among the authors linked to the combinatorial school similar definitions of mathematics, but saying that mathematics is the science of the forms of the quantities. No? That's different, but it's similar, and there are links there. So, Klugel. Mathematics is the science of the forms of quantities, that is, all the ways in which a quantity is composed from others. And then this definition is repeated in, well, Klugel is the author of this famous Germanic mathematical dictionary for the beginning of the 19th century, and it's repeated everywhere in his work. So, well, that's it. Let's talk about mathematics in Bolzano. And so, let's talk about what he understands by concepts and intuitions. So, in his work of 1810, he writes, mathematics and metaphysics, or philosophy, are the two main parts of our a priori knowledge. That's not to be there. But the former deals with the general conditions under which the existence of things is possible. We saw his definition about the conditions of possibility of things. And the later seeks to prove a priori the reality of certain objects, such as the freedom of God and the immortality of the soul. And then, in the same work, he writes, all ideas are either intuitions, that is, ideas of an individual, or concepts, ideas of something general. So one can see here where is going Bolzano, no? Because for sure, if mathematics is the science, yes, Abel.
Father.
Yeah.
Father Bolzano, because I think that is important in this point.
Yeah. So he's saying if mathematics deals precisely with concepts, with generals, there is no place for intuitions in mathematics. Not only that, but for him, intuitions precisely, he says, this concept of a priori intuition seems contradictory. I don't understand what you want to tell me when you said intuition a priori, no, in this sense. Because for him, it must be noticed, intuitions are necessarily empirical, and thus they are alien to mathematics.
They are?
Alien to mathematics, no? So he grounds the possibility, this is Cantu, of imaginary or ideal quantities on the independence from intuition and imagination. I'm going too fast. So, here Bolzano, for example, says, okay, let's think about a line, an infinite line. I have no pictorial image, which was an interpretation of Kant among Kantians of the time. For example, Michelsen, the translator of Euler to German. Well, it's not well known, but Michelsen, and Germanic also. But it was not the only one. It was common to understand the Kantian intuition as linked to pictorial images. No? So Bolzano says, I can't have a pictorial image of an infinite line, and still I can work with that idea, I can work with certain concepts. So that's why Cantu is saying this, that he grounds the possibility of imaginary and ideal quantities. And then Loew and Brodsky wrote that certain notions are introduced by which the domain of the respective discipline is narrowed down. Loew and Brodsky wrote this article, and I agree with them because they said their thesis is that Bolzano, at least his rein analytische Beweis, reflects a transition from a formula-centered way of doing mathematics to a concept-centered way of doing mathematics. So you can see this, we'll go to that work in particular, but you can see that in Bolzano's classification of mathematics, which is this one. So, yeah, I will read it. I don't know if I can. No, I don't think so. Yeah, sorry, but I will read it to you. Okay, perfect. So this is not precisely how Bolzano presents this classification in his book, because there's a mistake there. And I think it's better the way that Bloch does this. So for Bolzano, first, you have, so we saw his distinction between philosophy or metaphysics and mathematics, no? And then, so mathematics deals with free things, okay? As such, it says in the top. And so, general mathematics includes etiology. Is someone familiar with this? Etiology? Etiology. By the time it was familiar, but it was related to the diseases. I don't know if, yeah, I will go. Yeah, it was related to that, but there was another definition, which is the one that Bolzano is talking about. That is the science of the grounds. Okay? Yeah, I will go back to that, because later Bolzano thinks that etiology is not to be part of mathematics. It's to be what the textbooks, the Germanic textbooks of the 18th century, included at the beginning of the text. You can say the logic or the mathematical, on the mathematical method, but it should not be part of mathematics. But here Bolzano includes this, the science of the grounds, okay? Of the general grounds, because then you have temporal etiology, which is concerned with the cause. That's different. So let me say a couple of things more there. For the Leibnizian Wolffian tradition, there were some principles that were included among ontology, such as the principle of sufficient reason. Yeah? Well, Bolzano is including those here. So what those were for the Leibniz and Wolff, Bolzano is including them here. So he says, for example, he only published the first part of the Beiträge, okay? But the second part was written, it was not published. And in the second part, unpublished, he explains more this concept of etiology. And there he says, he presents a version of the principle of sufficient reason and says something like, anything I know has a ground that explains why I know it. That's the principle for Bolzano. And that principle is part of etiology. Okay? Well, it doesn't matter. Okay. So, anyway, you have arithmetic, algebra, analysis, and combinatorics, which is a surprise because only those authors that were taking into account what was going on with the combinatorial school would do something like this. No one else would include combinatorics among the general matrices. This is really surprising. And then you have special mathematics, and you have chronology, geometry, temporal etiology, mechanics, and those deals with unfree sensible things in abstracto, geometry and chronology, one in time, one in space, and then in concreto, no? And you have temporal etiology and mechanics. Well, this is Bolzano's classification of sciences. But what Loew and Roski said is really important because this is rooted on concepts. Yeah, and this shows that Bolzano is giving a crucial role to concepts in his conception of mathematics. And not only in his conception, as we will see, but in his way of doing mathematics. So, also, it should be noted what Bolzano said about foundations. And so, as I said before, at the beginning of his Beiträge, he wrote, a work on mathematical method is logic. And then he says something like, and therefore, there's no part for it here in mathematics. But I will say some things. And then he explains a couple of things. And as I said, etiology is the science of the general notion of ground, or groundlehre. And so can precede all of mathematics as an introduction. As I said before, this was what in the Germanic textbooks of the 18th century was included before talking about, for example, about numbers and quantities. No, they were talking about what mathematics was, what were definitions, axioms, and these kind of things. No, and then he wrote, in the realm of truth, that is the collection of all true judgments, a certain objective connection prevails, which is independent of our accidental and subjective recognition of it. This is important because, as we saw, his classification goes from general mathematics to particular mathematics. And what he's saying here, for those who ignore this, but Bolzano is normally considered one of the fathers of arithmetization by some authors, but one of the first authors that paved the way for the modern analysis. No, and for example, his work of 1817, his Reinanalytische Beweis, precisely shows a way of doing analysis in a pure way, no? Detached from geometry, among other things. But it's not only that. It is that he is also taking into account this idea, the idea that in the realm of truth, the collection of all true judgments, a certain objective connection prevails. And so, here are some of the principles that we can find in his works. So, for example, in the Considerations of 1804, he says, proper scientific proofs, demonstrations, should follow such order. First, then, the obviousness of a proposition does not free from the search for a proof of it or the understanding of its impossibility. This is crucial because for the previous Germanic mathematicians, for example, Wolf and company, an obvious proposition did not require a demonstration. And so Bolzano is criticizing this kind of doing mathematics. He says, even if it's obvious, as the intermediate value theorem, that was something that no one would question, but there was no pure proof showing the objective connection. No, that's what he is doing in his work of 1817. So he is doing that, but also, I will go to a couple of things more. Do not use alien concepts to the theory of the thesis to be proven. So you cannot use the concept of motion, for example, for geometrical propositions, for example. But not only that. For Bolzano, you cannot introduce considerations on the plane when talking about lines or angles. You don't need the plane for Bolzano to talk about lines or angles. Then you introduce the plane. But this is precisely why he criticizes Euclid, because he says, okay, Euclid, different from both, always tried to prove a proposition even if it was obvious. Okay, that he's praising there Euclid. But then he says, Euclid mixed everything. So you go to the elements and then you have suddenly a line, suddenly a triangle, and suddenly the plane is considered, but it's not gradual. It is not showing what Bolzano considers the objective connection of truths. And so also he says that there is at most one correct proof for any truth in the order, and proofs proceed from general to specific and from simple to complex propositions. So these are the ideas underlying his way of doing mathematics. So just to be clear of what's going on here, as I said before, in the Betrachtungen of 1804, he wrote, propositions about angles and ratios of straight lines to one another in triangles should not be proved by means of considerations of the plane, as the concept of motion should not be used to prove purely geometrical truths, as the geometrical truths should not be mixed with the analytical truths, because analysis pertains to general mathesis, and then geometry is in a second plane. So you cannot do this in the proofs for Bolzano. And then, in his work on the binomial theorem, he says, maybe in the future it should be decided that infinite or the differential are nothing but symbolic expressions, and that the method of proving truths using purely symbolic inventions is a method of proof which is indeed quite special, but is always correct and logically admissible. I'm quoting this because, as we saw at the beginning, in his paradoxes, he is saying that quantities are more than numbers, and that among those quantities that are not numbers are the fractions and those called irrational expressions. So, by this time, he is considered what we call imaginary numbers as symbolic expressions. They are not quantities, not numbers, they are sort of tools. Okay, this was common by the time, this consideration of symbolic expressions. And then, in his purely analytical proof, as I said before, is an attempt to provide a strict demonstration, a proof that situates the theorem in the objective order. And he rejects proof depending on geometrical truths, proofs using the concepts of time and motion, but then he rejects one proof of Lagrange, but for different reasons. Namely, he rejects this proof for depending on the decomposition into factors. What does this mean? What he's saying here is that, you know, his work of the 1817 deals with the intermediate value theorem. But, as the title makes explicit, he is talking also about what can be called the opposite sign theorem. No? And so at the beginning he says that, concerning this, Gauss offered a procedure, a correct procedure for the opposite sign theorem. And so what he's saying here is what I pointed out before, that you cannot use complex. Let me go back. Oh yeah, here at the end. Proofs proceed from general to specific and from simple to complex propositions. So what he's criticizing about Lagrange's proof is that he's mixing, he's going from a complex proposition to a simple proposition. And this is related to, well, that's Bolzano's point of view. But he's working according to what he considers this objective connection. Yeah, that's the one that I've already finished. So, just some final remarks. I have plenty of time. It should be noted, I said before that, for example, Paola Cantu points out about this U-turn in his definition, not a U-turn in his definition of mathematics. But it should be noted that in 1840, in his mathematical diaries, Bolzano had already changed his opinion on the definition of mathematics. And in fact, in a note, he describes general mathematics as the science of abstract quantities and special mathematics as concerned with a specific kind of quantity. This, to me, sounds more or less like something that Marco and Ferraro said about algebraic quantities in Lagrange. This notion of general abstract quantities, no? So, and this is not a coincidence for me, because Lagrange was linked in a way to the combinatorial school, and Bolzano, as I have mentioned, was linked in a way, in a theoretical way, if one wants to put it that way, also with the combinatorial school. So there are common points here in this conception of abstract quantities, general mathematics dealing with these abstract quantities. And well, there are also other things. I talked about this some weeks ago. For example, in his work on the binomial theorem, he's working with finite segments of infinite series, a procedure to avoid precisely working with the infinite, because he rejected infinite by that time. No, but also it must be stressed precisely that his program was partly rooted in inherited views and practices, but at the same time it had groundbreaking features. No, I said before this idea of Lev Ambroski, I quoted it. And finally, it is important to me to mention the pedagogical dimension of his program, because it is usually not studied, this part of Bolzano. But it is important because it reminds me, for example, when Dedekind, at the beginning of Stetigkeit, I think, when he says that in the late 1850s, when he was going to teach, he had to use geometric evidence that was didactically acceptable, but it was not rigorous, no? And so he went on working on this idea and developed, well, his principle of continuity, no? In a purely analytical way, no? This reminds me because Bolzano, this is also important for Bolzano. He says in his Rein analytische Beweis, we are in no way party to a purism so exaggerated that it demands that in its exposition one cannot even use an expression borrowed from another field. That is to say, he's saying that, okay, when we are teaching, when we are explaining, we can use the concept of motion to explain. But then when we are dealing with proofs, that's where we should not do that. So it's a way to make more accessible these things to students, for example. And this is important because what we understand for a textbook, it's not the same that it was understood in the 18th century and the 19th century. It's a different role among the mathematical community that this text had. And then also in his Wissenschaftslehre, he wrote, "A science is not always thought in keeping with its objective structure." So it was the same idea. So it was permissible, but we should just be careful when talking about proofs or talking about just how to show that something is to be done. No? Yeah, well, this was just a general panorama of his early conception of mathematics, but I hope you have enjoyed it. Thanks.
Carlos.
Me estoy habituando. Sí, me No, sí, sí, sí.
I have several remarks, but we will talk later. Just a simple question.
Yes.
Just a question. When you say that Bolzano is criticizing or disagreeing with Lagrange, exactly what? I mean, which text, which paper of Lagrange he's talking about? Because
so yeah,
you didn't say, I think.
No. I'm going
criticizing Lagrange. I'd like to know what.
Yeah. I'm going to read this. The fact remains that such a derivation could not be called a demonstration, in that the second proposition clearly expresses a much more complex truth than our present one. He's referring to the opposite sign theorem.
Yes, I know that he's talking about that. But by the way, it is, let's say, it's a particular version of the fundamental theorem of algebra.
Exactly.
Proving that an odd degree polynomial.
Exactly, that's the point.
That's the problem.
Yeah, that's the point.
I wanted to know which paper of Lagrange he was talking about.
Okay, that I don't know. I have to check the manuscript.
If it is the paper which I think he's reading, then Bolzano
is misunderstanding.
No, he's wrong, because the first one who made these critics toward the argument of the factorization is Lagrange himself.
Okay.
Lagrange himself says, I give this argument, but later he says, of course, this argument, this proof is misleading.
Okay.
So,
I have no idea.
That's what I wanted to know.
Yeah, I have no idea. I need to check it.
The proof of a journal proof of power through the development of the function?
No, exactly. It's not the theory of analytic functions. No. It's not the reflection of algebraic equations, which I talked about yesterday. It's on the
Which proof is misleading?
The one which uses the factorization theory in order to prove the existence of a real root.
Mm-hmm.
And why is it misleading? Because you are, before that, you are assuming that complex roots appear always in number third. I mean, in fact, what you are assuming is that if you have a complex root, then the A plus B plus the conjugate root.
Could it be?
The conjugate number, complex number is also which you cannot prove, because then you are assuming the form of the complex roots.
Mm-hmm.
That's what I was asking. Exactly that was I was asking. That's exactly what I was asking. Carmen.
Can you put your last slide back on?
Yeah.
I have a comment and a question.
On what?
The last two.
Okay, yeah.
Actually, yeah. I'm pretty sure that's how we teach today. That is, when we teach, we're allowed certain things that would not be admissible in a formal proof or a proof. So I just wanted to make that comment because it seems that Bolzano's conception of mathematics may seem to be, in his definitions at least, be very different from what we would expect an answer to that question to be today, but that bit is exactly like it is today.
Yeah.
Motion, time, drawings,
Sure.
lines, we use that.
Sure. Can I say a couple of, okay. So yeah, for sure. But then one have to consider that we're talking about the early 19th century, and that, for example, precisely, I did not talk about this because I was afraid of some commentary of Abel, but no, he's there. So I have plenty of time. So Schultz, an author that Bolzano is praising, prefers nominal definitions precisely to avoid the introduction, he says, of, for example, the notion of motion. So we're talking here about the first authors in the Germanic mathematical community making a distinction here, because this is not involved, neither in Kessner, neither in Segner or Kasten. But then you have authors like Schultz, Michelsen, Zimmermann. Michelsen, Zimmermann, an author linked to Schultz and to Kant at Königsberg. Then you have also Thibaut, professor of mathematics at Göttingen. So you have this author, or Martin Ohm. You have this Germanic mathematical community of the early 19th century beginning to think about this precisely. So Bolzano is one of these authors, but yeah, I agree. But then, if you put it in context, it's relevant this kind of reflections. No?
And I have my question.
Yeah.
Is how does he interpret that the last couple of words there? Another field.
Or
cannot even use an expression borrowed from another field. Because you mentioned as an example things that we could say, so if you're proving something in geometry, you shouldn't use something from mechanics.
Yeah, exactly.
But so if I'm proving something in analysis, can I use something from algebra?
Yeah.
Are those grouped together?
No.
How strict
No.
is that?
Yeah, exactly. But that's linked with that idea. What?
With the tree.
With the tree and the idea of simple and complex. So yeah, you can go from the general and use from here there, but not the other way. So that's why you cannot use geometry to analytical proofs, but then you can use analysis for geometry. No.
It's more than just from another field. It's sort of like having
From another branch. Yeah, I think so. Yeah.
Otro comentario, pregunta, Eduardo.
Thank you. I just want to say that the link between Bolzano and the combinatorial school is more than the theoretical link.
Yeah, sure.
Because this idea of symbolic expression and the manipulation, combinatorial manipulation of symbolic expressions, is the very main idea of the late combinatorial school program by Ullmann, for instance.
Okay.
It's very important to make the link with this idea. Is almost a combinatorialist here.
Yeah, sure, and that's why I was saying. Yeah, I agree. I mean, I was saying the way he worked when working on the binomial theorem precisely. I think that's also linked the way he's dealing there with the problems, the mathematical. I mean, his mathematical practice is,
Yes, it's in the same tradition.
Yeah, but there are also other things. That's the key issue with Bolzano. That you have that, but also this debate with the Kant and the Kantians, and it's a mixture of fronts. I don't know how to say it.
No importa, Germán.
Germán.
Gracias. Maybe my question is simple, but I don't know.
Oh, those are the...
I've always wondered what does simplicity and complexity mean.
Okay, yeah, sure.
And when Bolzano says you must have multiple propositions, like,
Sure. Good.
is it a subjective notion or is it...
Good question, because I avoid also that, all that, but so he talks about David Treger, the work of the 1810. He begins talking about the definition of mathematics, and then the second part is on the mathematical method, which I did not explain. But there, and then is the part devoted to Kant, no? A whole part devoted to Kant. But then, about mathematical method. So, for him, he says, we have been so grown, beginning by definitions. Definitions are not the first in mathematics. And then he says, what's first? Because definitions involve a composition of concepts, no? And this idea of composition is a key idea in Bolzano, because he says, what we have first are simple concepts, no? And then you have to remember the objects of thought that he was talking about. So we have simple concepts, and then we must have what he says, an insight about how these simple concepts will combine. And then we have designations. Rostock says it's circumscriptions, designations, it's whatever the translation you choose. But in any case, then you have definitions, and then you have, classifications, and then you have postulates, and then you have actions. And those are unprovable propositions which deal with necessity in the case of actions, or with possibility in the case of postulates. No? So he is thinking about these precisely. So, for example, and simple concept, an object of thought, the point for Bolzano, no? So the point is he says, it's a simple concept. You cannot define the point. You can only designate to try to understand. And from there, from this simple concept, then you go to the more complex idea of a system of 2 points, no? And then and so on. So he's thinking precisely about this when he's talking about simplicity and complexity. He's thinking about how mathematics should be constructed from simple concepts, not definitions, towards theorems and so on. No? Yeah.
Thank you.
Yeah.
La última pregunta, Marcos.
Oh.
If I understand well, you suggest, among other things, that there is a change of Bolzano's conception of mathematics, starting from a conception that is tied in some way to the problem of algebraic analysis by Lagrange and combinatorial school, to a conception that focuses on the notion of quantity.
Not precisely. My idea was that, what Paula Cantu says, I agree mostly with her. She says that, okay, he used later the traditional definition, but he changed the meaning of quantity. So he was able to embrace what his previous definition, combinatorics, for example, allow him to. No, I would not say that this is strictly a change, but yes, that there are differences between what later Bolzano is doing and what the early Bolzano is doing. And so this is reflect on not only on the notions as infinitely small quantities.
The question is not simply what you write, the style of mathematics that Bolzano developed.
Yeah.
age is certainly not Lagrange and not combinatorial. It's another sort of mathematics.
The later,
It's
yes.
conceptual mathematics,
Yeah. Okay,
so
sure.
if you think that there is a starting point that is connected to the combinatorial school, to the Lagrange program, it means that something changed there, independently of the definition.
Yeah, sure.
Why the question is, what made this change happen?
Oh, well, that I don't know. Precisely, I intend, and it's not a project only of me. So, for example, Ross and Tlifayova clearly said that in that work of 2016, they say, well, that something happened between 1817 and 1830. Something happened there. And we have his mathematical diaries, but no one is studying those. So I hope in a week I will be studying those manuscripts, and that's precisely my project, to see what happened there.
I repeated you the question in 2 weeks.
No, maybe a little bit more, if maybe because that's what I want to work precisely with Carmen. So maybe in a couple of years. But no, yeah, that's the question. What happened there, and how this transition was made? No? Okay.